people to hold their questions to the end. And I will introduce you, and I will say that there may be press in the room, so keep that in mind when... Great. Okay. All right.
Yeah. Okay. So it's loading in. So basically,
but it's moving, right?
It's moving.
So let's give it time.
Let's give it time.
People. Yeah. I wonder... I got up at 6 this morning. Ooh, that's on. So that is how motivated I was. Yeah, well, to be clear, had my opening remarks been at 8:30 this morning, I would have been working on slides. So I have the rest of the day to do that. All right, so let's see. Okay, it's 8:30, so I think I'm going to get started. All right. Good morning, everyone. It is 8:30, so we will get started. Welcome to the conference. We have a very exciting day of activities planned for you. So a couple of things about this tutorial. First of all, there will be a break about halfway through, so just keep that in mind. Secondly, if you could hold your questions until the end, because we are such a large group, that would be fantastic. When we get to the point of questions, there are 2 microphones, one over there in that aisle and one over there in that aisle. Also, there may be press in attendance, so please keep that in mind when you're asking your questions. Great. And with that, I am delighted to introduce Fernanda Villegas and Martin Wattenberg. I'm an enormous fan of their work, so it's a true honor to be introducing them here today and to have them here at the conference. For those of you who don't know them, Fernanda and Martin co-lead Google's PAIR, People and AI Research initiative, as part of Google Brain. And their work in machine learning focuses on transparency and interpretability, part of a broad agenda to improve human-AI collaboration, interaction. They're extremely well known for their contributions to social and collaborative visualization and for the systems they've created, which are used daily by millions of people. And as if that wasn't enough awesomeness, their visualization-based artwork has also been exhibited worldwide and is part of the permanent collection at the Museum of Modern Art in New York. And with that, I will hand over to them.
Thank you so much. Thank you, Hannah. Thank you. It's such an honor to be here. We were so excited that there would be a tutorial at NeurIPS about data visualization. So let's get started. We have a lot of ground to cover. And we just wanted to briefly introduce our team. Today we're going to talk some about our work, but not a whole lot. There will be a lot of work that was done outside of our team, and we're hoping to give a landscape. But these are the awesome folks that we work with at Google. Martin and I also co-lead, as Hannah said, the PAIR initiative, the People plus AI Research initiative at Google. And this aims to bring design thinking and HCI, human-computer interaction, to machine learning. And hopefully you will see a little bit of what we mean by that as we talk about some of the work we've done. So today's agenda, we're trying to hit a couple of things. One is, what is data visualization? How does it work? What are some of the best practices? So when you're thinking about creating data visualization and using data visualization in your own work, what could you do to make it work better? And then secondly, how has visualization been applied to machine learning? We're going to, as I said, do an overview of the landscape. Some of the things we're going to touch on very briefly because we feel like some of these things are well understood by the community, so we're not going to dwell on basics. And then we're also going to talk about a very special case that I think is very native to machine learning, which is high-dimensional data, massively high-dimensional data. And we're going to end up with some what we think are promising directions. The goals of this tutorial, the way we thought about them, are for you to understand the state of the art, so catch up on what some of the best practices are, what people are doing with data visualization in machine learning today. And then secondly, how do you apply this to your own work? We're going to talk about some reference tools and libraries and give you references to literature so that you can also become a visualizer. You can also create, hopefully, new techniques and better techniques. All right, so let's start diving in. What is data visualization? I'm sure that if you work with machine learning, you've come across data visualization. You know what it is. Basically, you are transforming data into visual encodings, right? What is this good for? It's good for a bunch of things, independently of machine learning. It's good for exploring when you don't have a question, you know exactly, but you just want to get a sense of the data. It's obviously good for scientific insight. In fact, this is a lot of its pedigree, comes from science. It's also good for communicating your results, very good for communicating your results, and also for education. We're going to touch on some of these use cases as we go along. Now, one of the things that a lot of people who work with visualization or use visualization don't usually think about, but we think it's really important, is how do you ensure it works well? How do you engage the visual system, our visual system, in really smart ways? How do you work organically with what our eyes do really well? And so how do you take advantage of things like pre-attentive processing? We're going to talk very briefly about some of these things, but this is like some of the most fascinating things behind visualizations that work well. Another question that we get sometimes is data visualization different from statistics? And it's not that they are completely separate animals. In fact, I think they are really beautifully complementary. But there are a few things that might be different. So for instance, when you're exploring with data visualization, a lot of times you don't have a specific question in mind. You just really want to get a sense of the lay of the land and what the shape of your data is, and you don't even know what question you want to ask. With classic statistics, a lot of times you may have a specific question you're hoping to analyze. And so that's one of the ways in which they could differ, even though we have an asterisk there saying, okay, in exploratory data analysis, which is part of statistics, you don't always have a question. But then you're also probably using visualization anyway, so you're kind of back to visualization. And as I said, I really think that there is a complementarity between visualization and statistics. So it could be that as a first pass, you look at your data from a visualization perspective, you get a sense of some interesting outliers or patterns, and then you start engaging with statistical analysis to be like, okay, but does this generalize? What's going on in the entire in my entire data set?
Okay, so let's talk a little bit about the history of visualization. I think one of the things that's important to realize is it's a very general technique, and it actually goes back quite a long way. And very briefly, let's talk about this. So one thing that I found fascinating when I first started to learn the history of the field is that many of the sort of standard business graphics, line charts, bar charts, pie charts, and so forth, were all invented by the same person, William Playfair, who I think, I think of him as an economist. Some of his most famous graphs are exactly like this one here, where he's showing sort of, in this case, the balance of trade and showing both sort of the deficit and surplus in a very beautiful way by comparing two line graphs. One of the funny things I discovered more recently is he was actually apparently a secret agent as part of his job. So that just makes him all the more cool and something, I think we can think of as a little bit more glamorous than the typical visualizer. Another person who I think pushed the field forward was Florence Nightingale. And the interesting thing here is that Florence Nightingale was sort of known for her work on the military battlefield, looking at, trying to see soldiers come in injured, try to make sure that they would not stay injured, that they would get better. And one of the things that she noticed is that, in fact, people were largely not dying from wounds they had sustained immediately on the battlefield, but things would get infected, they would get sick, and they would die from the sickness. And she realized that with the right kinds of sanitation and hygiene measures, you could save millions of lives. Now, the interesting thing is that when she tried to make this case, it actually didn't go over particularly well immediately. And so she really had to pitch it to people in charge, the top politicians. And the way she did this was with visualizations. So she created a number of things. What you see here is something she called the coxcomb chart. It's a kind of complicated pie chart. And it ended up being very effective in helping her make the case. And arguably, this is the best visualization ever if measured in terms of number of lives saved. There's another important lesson for visualizers as we look at this, which is that today, I think a lot of people who are very kind of uptight about proper graphic design would look at this and say it is not a good visualization. We'll talk later about different visual encodings, and you could make an argument that, she's not really using the optimal things here. That didn't matter. This visualization saved millions of lives, and I think it's an important lesson that, as we go into visualization, and as you try things out, it's much more important to focus on asking the right questions, on getting the right data, rather than feeling incredibly nervous about, exactly the right technique. It's much better to do it and to focus on the data. One final example of historical interest is W.E.B. Du Bois created this fantastic album of visualizations with his students, showing a wide variety of demographic data. And these, I think, are some of the earliest visualizations that I've seen that, it's sort of funny, almost function like a modern dashboard in the sense that they combine many, many different sort of types of data about the same theme in one image. And I think there's actually a lot that we can learn from this in terms of both sort of the purpose of visualization, and again, its efficacy in making a case, but also in combining data in various ways. Like, this is a very beautiful visualization that has very natural legends. It's like the legends are almost serving as a table. You see it's really nicely labeled. And it's actually a perfect example of how to combine many different visualizations in one place. Okay, so what is it that makes these work besides having the right data and sort of asking the right questions? Well, they're using our own visual system in ways that it maybe was not designed for. We're supposed to have vision so that we can, see an animal that's about to eat us and run away from it or whatever. We did not evolve to analyze data. But the truth is that the visual system, is very special. And I like to think of it like a GPU. It has all of these native abilities where it's incredibly fast, better than our general purpose brain. But they're very specialized as well. And so the whole game behind visualization is much like GPU programming, where you're taking something that, is made for video games originally, and you're repurposing it for something else. One consequence of this that I think is actually critical to realize is that all visualizations, as a result, involve compromises. It's not like we have this amazing data analysis part of our brain, but we're repurposing something that was not built for that. And again, that causes a lot of trade-offs. So let's talk about what those sort of primitive operations are in the GPU in our brain. How do these things work? So the idea is that you want to find visual encodings. You want to take data, transform it into vision, and those encodings will do a bunch of things. So the first thing is they guide the viewer's attention. The second is they communicate data. Now, it's interesting. Very often when you hear people talk about charting, they'll think just about this middle thing. They act like it's just about communicating data. But this is just one of several things it's good for. The third main thing you can do in a static operation is that you can let the viewer calculate with data. And I'll show some examples with that. It turns out your brain can do some amazing calculations very quickly. And then once you're on a computer, you can interactively explore data. And there's a whole set of frontiers beyond paper. Okay. So let's take a look at some examples. Let's talk about the example of you have wind data, and you want to show wind data across the world. This is something people have thought about for hundreds of years. I think the earliest example that I could find comes from Edmund Halley in the 1600s, and it's this map of trade winds in the ocean. And you can see what he's doing is he's basically doing something fairly reasonable. He's saying, I'm going to show the direction of wind with a vector that points in the right direction. It's static, but it actually works pretty well. Let's talk about how you might use this in a modern setting. Okay, so this is a visualization that Fernanda and I created as an art project many years ago. This is showing the wind across the United States right now. And you can see that the encoding we're using is very much like Edmund Halley's. However, what we're doing is adding motion as well. In fact, if you look at this legend down here, you'll see that the legend is actually not a static thing. It's moving like the whole thing. This is a very, very simple visualization. It is designed really for us. We created this as an art project, not a science project, even though it turns out later scientists became interested in this. And you can see that there's a sort of simplicity to it that's very nice. Okay, what about, let's see, go back. Okay, so let's look at a more complicated encoding that was done later. About a year after we created that visualization, someone named Cameron Beccario was inspired, and he created this globe visualization. And you can see he's doing a lot more encodings, and I think it's very interesting to sort of sift through this and take a look at all the things he's doing. So like us, he is using sort of motion and angle. So, we built on Edmund Halley. He's building up. He's adding in color here, which I think in this case indicates the scale of this. But we can actually add all sorts of other things. So we can say, let's look at particulate matter. And now it's going to show us all sorts of, dust and smoke. Again, using a color scale. You might ask, how did he choose those colors? We'll talk a little bit about that in a moment. You could overlay all sorts of other things. You could change projections in various ways, all sorts of crazy projections, in fact. And let's see, I think we can even get waves if we look in the right place. Let's see. Well, we won't show that. In the interest of time, I won't show all the things it can do. But you can see that essentially by layering various encodings, he's able to actually show more data on this. Okay. So let's talk about those encodings specifically. So there are many different types of ways that you can put numbers into images. You see some of them laid out here. There's certainly many more. And the whole game behind visualization is that each of these are good for various things. So for example, position and length are very good for communicating exact values, as is text, for instance. Certainly you can get things to the nth decimal point that way. What about ratios? Their length is really good. Whereas, position, area is somewhat okay. Color is just impossible to tell ratios. And this is sort of, it's this perceptual fact that your brain is kind of computing ratios. This is sort of what will help you decide between, for example, a bar chart and a line chart. Other things are good for drawing attention. Color is one of the first things we see when we go look at a visualization, and it tells us where we should be looking for next. Area is also a very good way to draw attention. Bigger things, much more prominent and draw your attention than smaller things. Color, I want to talk a little bit about, just because this is something that in some ways is one of the best understood phenomena, or encodings, and it's actually very subtle. So starting a couple decades ago, Rogowitz and Trainish were some of the people who really started doing this. people started asking, what is the right way, if you are showing numeric data with color, that you should show it? Now, an interesting question is, why are you showing numeric data using color? Because we just talked about how things like position, length, and so forth are so much better for communicating numbers. On the other hand, if you remember back to that wind map that I showed, the final one on the globe, the point there is that if you wanted to show something like temperature, pressure, or so forth, you'd already used up all your spatial dimensions. So color was essentially one of the few things you had left. And for this reason, color is very important. So Rogowitz and Trainish did a series of careful studies where they would take the same data, in this case I think it's an MRI scan, they would sort of display it using all sorts of different color scales, and they came to sort of some interesting conclusions. So one is that they found that for high frequency components, luminance is the best thing to is sort of much easier to see, and you can essentially make sense of numbers best that way. Hue is actually somewhat better for low-frequency components. One thing that they did discover, though, even though there's no best scale, is that in many ways a rainbow scale, one of the most popular things, is actually really bad, that it has all sorts of weird optical illusions that occur in it. Nonetheless, decades later, people still use it. Practically speaking, so how do you make sense of all of these different types of colors? So there's a lot of theory, and one of the things that I would say is that a great way to use these things in practice is to go to a site called Color Brewer, and this was created by Cynthia Brewer. She's a cartographer. It's colorbrewer2.org, and it's actually a very beautiful site on a number of levels. So one thing that's cool is it will let you try out different palettes in sort of realistic settings. So what we're showing here is she has kind of a sample set of data at what looks like maybe city level or county level, a map. And then you can try out different scales and see what they look like. These are sort of multi-hue. You can try single hue. These are all sequential scales in which you've got some number that's monotonically sort of increasing. That's all that you care about. You could also try different diverging scales. So if sometimes there's a special unit, for example, in many cases, positive numbers and negative numbers mean very, very different things. And in those cases, you might want a diverging scale in which two ends of the scale look very different. You can also try different qualitative scales where maybe you don't want to have any sense of a sequence. And in that case, you want a set of colors that doesn't convey any sort of sequence in the same way that these ones do. So as both a practical tool and a way to learn about these colors, strong recommendation for the Color Brewer site. Yeah.
So just one more thing that I think is really important here. When you're talking about categorical data or these diverging palettes, one of the tricks is to make sure that you choose a color palette where one color doesn't look more important than the other, right? One color should not pop up and the others recede, because that can be perceived as one category being more important than the other. So that's why having tools like Color Brewer is really helpful, because the palette has been balanced from a perceptual perspective to make sure that everything kind of looks like it has the same importance.
Okay. Okay. And the thing I would emphasize is that this is a genuinely subtle art, picking the right color. And in fact, there's been very active research in the visualization community to this day. One thing I would just sort of point out as an interesting paper, if you do want to read more about this, is this recent paper from Kai. And they tested a whole bunch of color scales that had been put together by people who had, knew something about perception, plus the rainbow color scale, just to kind of bash it. And they did a wide variety of sort of human subject studies, and it essentially confirms the rainbow color scale is not very good. Other ones are better, but it's a subtle art, and it's hard to find significant differences between the top ones. One thing that's critical, though, is all of these color scales kind of collapse in a crazy way if you're colorblind. And it's important to remember that actually a fairly significant number of people have trouble in some aspect of color blindness. Most typically, sort of red-green color blindness is super common. Something like 8 to 10% of men have that. And if you have that kind of color blindness, this is exactly what all of these beautiful color scales look like to you. And so it's important, if you are making a general tool, something that's not just for you to look at, but something that's very general, to think hard about what is a safe thing to do. So for instance, there's the blue-orange scale down here, and you can see that actually survives pretty well for a colorblind person, whereas some of these other things, you know, certainly like the rainbow map doesn't look good at all, and some of the other things are very hard. Okay.
All right, so now let's talk a little bit about one of my favorite things, one of my favorite superpowers in data visualization. It's what we call pre-attentive processing. And it goes back to a little bit to what Martin was saying about our mind function, our visual system functioning like a GPU. It turns out that we're really good, if we're giving the right stimuli, I'm going to go back a little bit. If we're giving the right kind of visual stimuli, our visual system just works super fast, incredibly fast, faster than you moving your eyes, okay? So to give you an example of this, let's look at these numbers and let's count the fives, number fives. And now, let's count the fives again, okay? So this is how fast it is. As long as we encode the stimuli in a way that takes advantage of this pre-processing power we have, it just works. You don't even have to try. So how do we do this? It turns out that there is theory behind this, that there are certain things we are acutely aware of visually. One of them is color, just like what you just saw with the number fives. But there are other things too. There are differences in shapes, differences in alignment. There's a bunch of different things you can use that will just work incredibly fast for your viewers.
I want to just insert something as we talk about this, which is that it doesn't mean that all of these are equally good. So one thing that is pre-attentive, for example, is sharpness versus blurriness. And in fact, that has been explored as something that is a way of encoding data. I would say if you absolutely have to, you could consider that, but if not, be careful because it turns out to be incredibly fatiguing to look at all the blurry stuff on the screen if you do that. So this is an example of the type of trade-off that you see in visualizations.
Absolutely. And so, and one of the things that you get for free with these kinds of visual encodings is that, in a sense, no matter how many distractors you have, certain things are going to pop up really, really fast. So things like color, again, as long as you choose the right color palette, is going to pop up really, really well for people. Shape also tends to be one of those things. But again, even here, for me, as I look at the example on color versus the example on shape, color for me works way faster, way better than shape. So again, these trade-offs that Martin is talking about are really important. And chances are that your visualization is never going to be as simple as this, right? It's probably going to have multiple dimensions. And so, again, things are always a trade-off between these visual stimuli, your visual encodings, right? But also everything on the page, everything that you're showing at once. And so this is something that you have to constantly keep in mind. Just a very, very simple thing to do if you are creating a visualization and you are unsure how well things are working, show it to other people. Show it to people who don't know your data, don't know what you're trying to look at. Ask them, is this working for you? What do you see here? Okay? Here's an example. This is not about a visualization of data, but this is a really complicated diagram of parts of a machine. They're all labeled. And so if I were to ask you, okay, can you find number, and they're numbered, right? There are hundreds of parts. If I were to ask you, can you find number 57? It takes a while, right? One thing you could do is to layer things. So now I'm using 2 different colors. And again, it's still a ton of stuff. It's not going to just, number 57 is not going to pop up to me. But it's going to be much faster for me to just be like, oh, now I'm paying attention to numbers. So I'm only paying attention to red things. Okay. Think about this as you're thinking about layering multiple pieces of information on your visualization.
Okay, what else can you do? Well, your brain can calculate with visual information. There's a whole set of perceptual research, and you can also kind of sense this in yourself if you introspect. One thing that is kind of fascinating is a set of work done by Dan Ariely, where he showed that you can average visual variables. So for example, if you see a whole bunch of circles and then ask a person to compare, show a person a single circle and say, is that single circle bigger or smaller than the average size of that set? People are extraordinarily accurate at this, way more so than you would expect. And they can do it very, very quickly. And it's an example, basically, of something you get for free. It's like, wow, we just have this calculator in our head that, if I gave you a whole set of numbers written down and asked you to calculate the average, it would be kind of hard. But your eye can do this very quickly. You can use this to do weighted averages as well. And here I'm going to show you, rather than a piece of psychology, I'm going to show you a visualization, I hope.
Cursor all the way up.
Okay. Whoa. Chrome, come back.
No. Hang on. Just try this.
Okay.
Is it not loading?
We're hoping it's good. Ah, there we go. Okay. Good. The internet gods have smiled on us. Okay. So this is a visualization of the stock market. This is something, there's actually a whole tradition of visualizing the stock market in this way, which I'm fond of because it's one of the places where I started my career. But this is not created by either of us. There, okay. Gone, all right. And what you're seeing is essentially hundreds of publicly traded companies. Each rectangle represents a company. The area of a rectangle represents the market capitalization. The color tells you how it's doing in the market today. So I'm happy to say the market overall looks sort of reasonable. Green is good, meaning it's gone up. Red means it's gone down. I think this would be an example of something where you could quibble with the color scale. This red-green color scale, although it is classic for Wall Street, is very bad for people who are colorblind. So were I creating something like this, in fact, I was doing things like this at one point, we'd always have a sort of blue-orange or blue-green, blue-yellow color scale as well. But why does this work? Well, one of the things that's nice about this is that all of these companies have been arranged by sector and by subsector. And so that means that you can take a look at this and immediately see patterns. You can say, aha, okay, so actually the tech companies are doing pretty well overall. You sort of average that out to green. But then you can also see, wait, there's one little section that as a whole is not doing that well. And meanwhile, there's a bunch of very mixed activity up here in basic materials and so forth. So this technique, called a tree map, uses your eye's ability to see these sort of averages, essentially, and do a lot of calculations very quickly. Again, if you compare this to the alternative, looking at the stock quote pages in an old-fashioned printed newspaper, it would be not nearly as good. Okay, so that is weighted averages. Other things we can do. So there's a famous diagram in astronomy, the Hertzsprung-Russell diagram, that essentially is plotting for stars luminosity versus heat. And various versions of this diagram have existed for more than 100 years. This is actually, I think, one of the very first scatter plots used scientifically. You see a modern version here. Now, what's interesting about this is that when you make this plot, you see a very clear pattern, right? There's this sort of long thing here. Is typically astronomers call it the main sequence. There's many, many stars in this area, but it's not a line. It's a little bit, wavy. And then there are these clusters up here, and then there's actually a very sparse sequence down there that you can find. And your eye just picks this up immediately. It's like you see this probability distribution essentially right away, and you don't see this as a set of dots. You really do see this as okay, it's very dense here, it's less dense there. Really, your brain is essentially doing kernel density estimation, and it's doing it for free. So again, something that you can take advantage of very effectively. Okay, the final thing is, how do visualizations work on computers? What is added beyond the static kind of image we have? And there are a couple of key things. Interaction is the main one, and then also on the web, helping people converse and collaborate. We won't be talking about that as much, but I do want to talk a little bit about interaction. So there are a couple of ways of thinking about interaction. One of my favorite practical things, again, is more than 20 years old. It comes from Ben Schneiderman. He calls it a mantra, that when you are thinking about a visualization, you think, okay, I'm going to design this so that people get an overview first, then they can zoom and filter, and then they get details on demand if they want. And as we show visualizations today, we will actually refer back to this at various points. It's funny, he actually thought this was so important that he wrote this article where he had repeated this mantra over and over again for every project where he's forgotten it and was unhappy. I'm going to show a demo of, we might have that already. Yeah, it's loading in. Okay, and let's go full screen. Okay, that shows us. So here we have a map that is showing essentially every person in the United States. This is based on census data and from 2010. And you can see right away you get this overview. You sort of see the shape of the US. By the way, we looked for one for Canada and unfortunately it doesn't exist. There is one for Brazil though. What you're seeing here is each dot represents a person, and the location of the dot, it's not quite down to the house level. I think that would probably be an invasion of privacy, and the census doesn't make that level of data available for 2010. But it's very close. It's down essentially to a neighborhood level. And the color of the dot tells you that the race that the person who filled out the census form identified with. And immediately, just looking at this, you get this overview as you can start to see, like, oh, okay, there's these broad swaths of blue in the middle of the country that corresponds to white. But you can see sort of these much more colorful areas where there's cities. Let's see, I think a bunch of people are from California, I'm guessing. So now we've seen the overview. Let's zoom in. And you actually can start to see, we'll go to San Francisco, for example. And you can start to see actually very strong patterns of, it's not equally mixed. There's a clear sort of housing segregation. Yeah, I'll do that in a moment. If I add the map labels, you can actually get some streets. You can start to see neighborhoods. And you can start to see essentially a lot of the history of the United States, and including some fairly unfortunate history, written in to the census that we see today. And this is something that I think is an incredibly interesting map. You can see all sorts of, every city has its own particular thumbprint. You can see Chicago is another very, very interesting one. And the idea is that you can very seamlessly move between the big view of the whole country and the small view, all the way down to sort of individual dots. And if you do want details, if you do want these labels, you can just add them in. And I think this is sort of a great example of that type of transition. Okay. All right.
Can you just say something?
Yeah, go ahead.
There's just one more thing I want to add here that I think is interesting is this visualization is, again, taking advantage of those superpowers. So I just took out all of the map information. There is no map here, literally. It's a bunch of dots on white. And yet it looks like a map, right? Because our eyes are doing the gestalt thing of closure. So when I start putting things close enough, our eyes just fill in the blanks. That's why we can see shapes. But basically, I'm just drawing a bunch of dots on a white background. I don't have a map, and yet it totally looks like a map, right? So think about the power again. You cannot not see this. You see it. Okay.
Okay. All right. Okay. So let's talk a little bit about how you put these together. One thing that we thought would be really nice to do, actually, is to talk about tables of numbers, because every time we've talked to machine learning teams, and we spent a lot of time inside of Google talking to different teams working with ML in various forms, and sometimes they come to us and ask for visualizations. Often they've seen something very fancy and they want something very fancy. But quite often you look at what they're actually seeing day to day, and it's tables of numbers, and those numbers are important, and they're really hard to read. And so one of the things that I believe is that almost the first thing you should try in thinking about making any data display you have better is to redesign your tables. And there's actually a beautiful video from a place called Dark Horse Analytics that we'd like to show that sort of illustrates this about as well as anything I've ever seen. Let's see. We're going to hope the internet gods will favor us once again on this. Okay. So they start out with this bad table. They remove colors, remove grid lines. In fact, they remove all those fills. No borders. Watch this alignment. It's like you breathe easy when things get aligned. Ah. Yes, let's resize those columns, please. Oh, look, the white space is working for us. Look at them rounding the numbers. Look how much better that is. Round your numbers, folks. They don't like that font. That's not the worst thing in here. And then you can add emphasis once you have things. Yeah.
We're going to leave it again because it's fast.
Look how bad that is. But that's normal, right? Like that looked like a normal thing.
But this is the end table.
Yeah.
So think about how many things they removed from the default. They left align some columns and right align others. That's interesting. They right align numbers because it's easier visually for me to scan numbers that are right aligned. But it's easier for me to scan text that is left aligned.
Yeah, so even though this is, again, probably not the most glamorous visualization you've seen all day, I do think that this is like 90% of the time you can get a genuine improvement in any data display system you have by just following these principles. All right.
All right, so now some more common techniques that we think could be very helpful in machine learning land. When you have a ton of data, high density, there's something called small multiples, which is basically you repeat your chart over and over again for each moment that is important. So what we're showing here is a visualization that was on the New York Times for drought in the US over decades. So each one of these rows is a decade's worth of drought in the US, okay? And the question that the article was asking is, are we having more drought today than we've had in the past? You be the judge. So there is a temporal dimension here, but they unpacked this temporal dimension so that you could have this matrix, okay? So you can keep scanning over and over again. Now, another thing I want to call attention to here, think about the color. I have a background color that is very faint so that my map of the US recedes into the background because, you know what, my map is not the most important thing. It is the context, so it is important. But the drought information is what I want to pop up. And so the really highlighting saturated color is only for the drought. So now I'm playing with receding to the background and coming to the foreground with the highlighted color. Here's another one that works very much the same way. This is patterns of birds, what exists today in blue, and probably where they will exist in many years if climate change continues. But again, think about how many numbers worth of data this is. And again, the same kind of visual encoding with the map very faint in the background to give me context, and these now 2 layers of data at the same time. The last thing I want to call attention to is this notion of faceting. So we're going to go to this New York Times. By the way, the New York Times is an amazing powerhouse of data visualization. And so I highly recommend looking at some of the work they do. But this is basically visualizing a ton of companies across the U.S. and how much what are the tax rates for these companies and how much variance there is in the tax rates. Each one of these circles is a company, okay, sized differently and I can tell you here what it is because it has a legend. Legends, yes, important. Labels, important. Always, always label your data and explain the legend. So the market capitalization, I didn't have to memorize this. I could just come here and look before I tell you. The color is also here, right? But look at this interesting thing that they did with the color. They are already showing me a distribution that goes from the lowest tax rate on the left to the highest tax rates on the right. So just by looking at this distribution, I know that things are going up the further to the right they are. But then they went one step further. They binned things with colors for me. Okay? So these colors are just binning things. And the binning is explained here. All right? They did another thing that is just helping me. They actually calculated here the overall average tax rate for the entire distribution. Right? So again, they are packing a ton of information into this graph. There's a bunch more explanation here. But then there's this beautiful thing they do, which is these are all the companies together. Now I'm going to click this button, and I'm going to see it by industry. And it just does this beautiful waterfall by industry. Now, again, they are showing me the distribution, but now they are calculating that average line for each one of these industry sections, which is awesome. And they have a little commentary for each one of those too, showing me things that are interesting. They are also arranging these, by the way, in crescent order, right? So I'm going from utilities, which has the lowest average, to insurance, which has the highest average. Okay? So really nicely done, ton of information here. Okay. Okay. Oh.
Okay. So all of this so far has been just general visualization information. Let's talk a little bit about visualization in machine learning. So what you see here is the visualization pipeline. This is a slide that taken from Yannick Asobba, someone in our group, who actually realized that if you look at the pipeline of machine learning, you can identify where visualization may be especially helpful. It's thinking about sort of acquiring data, it's as you implement a model, as you between training, and when you deploy it for monitoring. And so that's essentially a framework that we like to use as we talk through machine learning. So we're going to talk a lot about visualizing training data. We will very, very briefly talk about model performance. And then we'll talk about interpretability and model inspection, kind of trying to crack open the so-called black box. We'll think about high-dimensional data. And then I think education and communication, scientific communication is incredibly important in a lot of ways. And visualization is a perfect match for that particular task.
All right, so visualizing training data. One of the things, this is some work we did a while ago, and we realized that there is a dearth of good tools for just looking at your data, your training data. So we looked at how do you visualize very simply something like CFAR 10? And so we created this. Let me see if I can enter full screen here. So this is called Facets, and it's nothing more than looking at your pictures from CFAR 10. So I have all my images here. This is not the data set in its entirety, but it's a good chunk of the data set. And I'm just organizing my pictures by the categories in CFAR 10. Immediately, I can see things like, oh, differences in hues. Okay, makes sense. Airplanes are more probably going to be in the blue zone, and so are ships, versus birds, for instance. But then the other thing I can do is I can start playing with this. I can start zooming in very quickly and just making sure that my data set looks right and that, half of my data set isn't blank, for instance. Even that at this point is interesting. Another thing I can do is I can start playing some games. So now I want to see the same visualization, the same data, but I want to see the hue distribution within each one of the classes. And then again, I can see, okay, all right, airplanes and ships, big bulge of blue there, versus the animals here, which are, earth tones. Makes sense. Other things we can start to do is to create a confusion matrix. And this is so cool. This is the kind of audience I don't have to explain a confusion matrix to. So good news, my diagonal is highly populated. That's awesome. But now what I want to do is I want to take out that diagonal. I want to take out all the right stuff. And boom, I have all the mistakes that my system has made. And immediately I can see that there are 2 cells here that are highly populated, right? And they happen to be the cells that are mixing up cats and dogs, okay? So that tells me something about the kinds of mistakes my system is starting to make. Go away. All right. Another thing I want to show is this visualization of the softmax layer. And what's happening here, I just want to see the distribution. And so the more to the right an image is, the more certain my system is that that image is indeed an airplane or a dog or a cat. But likewise, the more to the left, the more likely, the more certain my system is that that image is not an airplane or not a cat, okay? And so we were immediately looked at this, we're like, oh, cats. That is the biggest one that my system is very, very sure about. So let's look into cats. So we zoom in into cats. And remember, this is CFAR 10, so thousands of people have looked and played with this data set. And so did we. And then we started looking, and we're like, oh, look, that's interesting. These are the cats my system is very sure are not cats. And can you spot towards the bottom, hint, a non-cat? Over here. This guy has been labeled by humans as a cat, and my system is very, very sure it's a frog. And I have to give it to my system. I think it's a frog. I don't think it's a cat at all. I think it's a mistake, right? So this is interesting because just by visualizing and making your data set very accessible, chances are you could start spotting more, mistakes. And so this is one example of how you might want to use visualization to look at your training data.
I'm just going to interject something, which is that this really illustrates very well this idea of overview first, zoom, in this case very literally zoom, filter, and then the details on demand to see the individual frog.
Good point. And Facets is available. It's open source, and so please feel free to download it, use it, make it better. That's the idea there. I want to call your attention to something I think was very cool that Quick Draw did. This is not our team's work. Everybody knows Quick Draw here? Some people? Okay. For those of you who have not heard of this, please do not play it now. It's a game. You go
and it makes noise.
And it makes noise, yeah. And it's going to make our internet really slow. But basically, you're playing Pictionary with a machine learning system. It gives you 20 seconds. It gives you something to draw and 20 seconds to draw, and it keeps trying to guess what it is that you're drawing. Okay. And so what happens is that this went viral, and it created a huge data set of drawings, of doodles. And they the team open sourced this data set. And it's really cool because you can be like, ooh, onion. Okay, I click here. I can see all the onions that people are, drawing, and they actually show me the strokes and everything. But one of the things that this allowed the team to do, and because they open sourced, other people outside of the team started doing this too, is do some data analysis of the training data. So things like if you could overlay all of the cats that people from different countries have drawn, you get things like these, and you can get a sense that, yeah, people draw cats very, very similarly across the globe. That's great. Turns out that that's not true for everything. Turns out that chairs, for instance, are drawn very differently in Korea than in Brazil, where I'm from. So I'm like, who knew that? This one I find really interesting, outlets, and it's just very illustrative of where people are coming from. So again, this is another kind of visualization for looking at your data set and starting to think about what are some of the questions that might be interesting there. This is the same data set, and they were looking at fish, the category fish. And so remember small multiples? These are small multiples for each country, okay? And it's overlays. And the cool thing is that you can see that in some countries, the fish definitely face one direction, okay? And it's usually to the left. Turkey turns out to be the only country where the fish very definitely faces the other direction. Okay, that's interesting. Nobody knew this. But again, think about things like if you're training your system and you want to be aware of biases, right? This would start to give you some notion of, oh, is my fish always facing one way versus the other? Am I covering a ton of ground here? Okay, so this is the last note we want to very briefly say before we break. Performance monitoring is probably the place where most of us see visualization on a day-to-day basis, right? Because it's basically a ton of line charts. It's a lot of charts. You are constantly trying to make sure that your system is converging, it's doing what it's supposed to do. And a lot of basics work here. Line charts, yay, go line charts, awesome. So we're not going to dwell a whole lot on monitoring dashboards. We're just saying, yes, visualization, super useful. Continue to use visualization. Basics apply here. It's all good. I think we're going to stop for a break here, 10 minutes, and then we come back. At
Interpretability, high dimension.
9:35. Okay, so we're coming back at 9:35 for interpretability. You do not want to miss that.
High dimensional data, all sorts of good stuff.
Yeah.
All right.
Thanks.
Thanks. people told me I need to get closer to the mic, and I've adjusted it a little bit up so
Okay.
it's between us.
Okay, sounds good. Sounds good.
One person's like at different heights, so feel free to move the microphone if I move it.
Sounds good. And feel good.
Yeah.
We'll just be like, okay. Okay, and we're going to start back with what I think is one of the most exciting areas for data visualization in machine learning, which is interpretability and model inspection. And I feel like here there are many different kinds of approaches and many different kinds of questions that people are asking when they ask about what are their models doing, how are they behaving. And so there are different sections to this part. So the first thing we're going to talk about, again, kind of briefly, is convolutional neural nets. And we're thinking about the interpretation of image classification systems here as a petri dish, right? As we all know, image classifiers are quite effective in practice, but exactly what they're doing and how they're doing it is kind of mysterious. And then they have failures that add to that mystery, right? For example, adversarial examples. But still, they're way easier to inspect than our image classifiers in our human brain. So that's good news, I guess. And I guess another thing is, since they are visual, right? They are image classifiers. It's kind of natural to try to use visualization to understand what it is that they're doing. So some of the things that I'm sure a lot of you have seen in the literature that these kinds of visualization systems try to do is trying to understand what features are these networks really using. Do individual units have meaning? And this is really interesting because I feel like there's a class of researchers who are like, yes, let's inspect individual units. And other class of researchers was like, no, what are you doing? So there are different camps. What roles are played by different layers of the network? So if you start taking into account the architecture of the network, and then how are high-level concepts built from lower-level concepts, okay? So one of the first things and one of the most ubiquitous things that we see are saliency maps, right? And these are those kinds of maps where you were trying to understand which pixels are the most relevant for some classification. And there are a number of different methods for getting at saliency maps. And some of them are looking at gradients, integrated gradients. You can have your pick. There are many, many different versions of saliency maps. So the idea with saliency maps is to consider the sensitivity of a class to each pixel, right? And there, as I was saying, there are many different ways that people have extended that initial idea, that basic idea. There's layer-wise relevance, there's integrated gradients, guided backprop, etc. One thing to keep in mind, though, is that these can be sometimes deceiving. You know, they tend to be visually noisy. It's sometimes easy to project onto them what you think you are seeing, right? Ooh, I see the dog face here. Ooh, I see the eyes, and sometimes you do. But is it really that it's paying attention to eyes and ears, or is it that it's doing an edge detection kind of thing? And so there has been work that is trying to tease these things apart, and it's noisy. It's not clear that these things are doing what we want them to do. So just a word of caution there. Other kind of work that I'm imagining the community here is very familiar with is this notion of maximizing neuron response, right? So what are the images that maximized the response from arbitrary neurons? And you start to see these interesting kind of building blocks. Oh, you know, there are stripy patterns, or there are colors that really activate a certain neuron. And so part of what you're trying to do there is to try to understand, is there anything that we can interpret from these images that are maximally that are maximizing the response from a given neuron? There's also, you can do the same kind of thing with relationship to entire classes, right? So you can say, okay, the pelican class, what are the kinds of things that activates the most response to that kind of class? And there is a little bit of art there. It's not just, otherwise these images can kind of look random, like noise, like visual noise. So there's a lot of art into making sure that you get something that starts to look humanly interpretable. One of the visualizations that I think has been super helpful, and this has been done a while ago, is DrawNet by Antonio Torralba and partners at MIT. This was one of the first visualizations that try to follow this notion of activation. What are the building blocks at the very top there? What are the most basic visual building blocks that activate neurons? And then each one of these rows is a layer, and each one of these dots is a different neuron in that layer. And so you can click on different neurons and see. Actually, let me see. Oh, let me see if I can give a very quick demo of this. Do we have it? No, we don't have it. If it takes too long, I will move on. I'll move on. But one of the things that I think is really nice about this visualization is that I've seen this being used to explain to people outside of the machine learning community how neural net works, how these systems work, and how they kind of piece together from building blocks all the way into complicated scenes or entire concepts like a flower, a dog, and so forth. And so there is a lot of power in a visualization like this that tries to connect these concepts. And then obviously we have things like deep dream. In a sense, this is like the culmination of trying to activate the heck out of these neurons. And then we come to places where, like this paper here called The Building Blocks of Interpretability. And this was a paper on Distill that try to bring together a lot of these different approaches and say, oh, okay, if we start looking at these different activations, notice here, just referring back to some of the things we were talking about before, they are making use of small multiples. They are labeling a lot of what they're doing. A lot of this is very interactive. So they really use to the full this notion of, I'm going to interact with this very complicated space of data to try to understand how are these systems working. And they have a whole system that lays out kind of in their minds what the interpretability landscape is like, and what kinds of insights you might want to get by doing different kinds of approaches. Here's another work from MIT where they are going from visualizations to interpretation. So they are taking this idea of you have a scene, a complex scene that has been human labeled, and there's more than one concept per image. And then you visualize a certain, you look at the top activated images for some unit, okay? So this top row here happens to be faces. And then you try to look at what is the concept that it most closely matches to, and in this case it's head. So it starts to bridge that gap between activations, visual activations, and actual concepts that we can interpret and we can understand. And so this seems like an interesting way of bridging not only what's happening visually and what's happening with the pixels, but getting into more of the semantic and the conceptual sense. Okay, so RNNs. Here, one of the works that we admire a lot is Karpathy's work. That again, it's kind of old at this point, but we thought did an amazing job of looking at visualizing text sequences, and again trying to understand. Oh, if you activate different cells, what kinds of can you interpret them? And granted, most of the cells you can't interpret. They don't give you any pattern that kind of makes sense, but some of them, I think it was around 5% of them, did. So here's a couple of examples of those. The top one, this one here that looks like a gradient, is a cell that's sensitive to position in the line of text, okay? And then the bottom one is a cell that turns on inside quotes. So you open the quotes here, and it turns red, and then you close the quotes, and it goes back, right? So it's very, very sensitive to these concepts.
I'm going to interject a little visualization note here, is to look at what's going on in this. Like, this is a very beautiful, simple visualization, but first of all, the color scale is very friendly to people who are red-green colorblind. The other thing is looking at the fact that he used color here is really nice because it layers right on top of the data. And so it's a good example of, even though color is typically not considered the right way to show quantitative data in, say, a graph or something, this is actually really good. It's a good example of making the right trade-off to make the visualization work.
Yeah, and you brought up a really good point that I want to emphasize, is whenever you're visualizing something, if you can always go back to your raw data and show that to the user, in this case the raw data is the text, the better your visualization is going to be, because you're going to bridge that gap between like some analytical framing or visual encoding you're doing and the messiness of the raw and exactly what it is you're encoding. So take advantage of that as much as you can. And a final example here of a cell that activates inside if statements. So it really cares about if statements, and then it flips back. This is another example. This is a much more recent example of visualizing RNN. So this is Seek to Seek Viz, and it's by Hendrik Strobelt. And here, what he was looking at, he was really interested in building a visual tool that allowed researchers to debug a translation system. Okay, so what he has a ton of different visualizations here put together, and they are all interacting with each other. And it starts here at the top where he enters a sentence in German. And so this is what the encoder sees here is in German. The decoder is looking at English, but it's giving you, for each one of its words in that sequence, it's giving you a notion of all the other words it didn't choose. And Hendrik is overlaying a bar chart to give you a sense of the probability. So you can see that for some of these choices here, the choice was very close. The probability was very close. So this starts to not only remind you of the output of the system, but it goes one layer down and starts to show you, yeah, but I was kind of confused about, these two words, or I could have chosen the other one, or no, I was very, very certain of my top choice there. It also shows you this tree structure for all the different paths it could have followed in this translation, and it highlights for you in a thicker way here the path it chose. Again, trying to give you a sense of all the different choices it was considering. And then here, it takes each one of these words in the target language, and it looks at the embedding spaces. But not only that, it also gives you a notion of the nearest neighbors for each one of these words that it was looking at. So again, giving you the target, but always giving you the context and allowing you to kind of try to understand oh, do I agree with what it's doing? Do I think there's a problem? How do I debug this thing? Okay? I believe this is open source, right? I think it's open source. And then finally, this is one visualization that was looking at games. And very complicated. You can see there's a ton of visualizations here, right? And again, it was one of these connected views where you would highlight one graph and the others would respond to whatever it is that you were looking at. And one of the things we wanted to call attention to, if you're interested in visualization, is this VAST. VAST is a conference, visual analytics conference, and they're starting to do a lot of work on visualizations for machine learning, and so this work was published there.
Cool. Okay, so let's talk a little bit about high-dimensional data. So this is a sort of critical part of machine learning that, in a sense, it's the lingua franca. This is how so many things in a complex model can be reduced to a vector in high-dimensional space. And so the question about visualizing this kind of data becomes critical. Unfortunately, it's really tough, and it's tough for the unfortunate reason that it's impossible. Like, you just can't do it right. And the familiar analogy is with a map, that if we try to project the globe onto 2 dimensions, there are lots of different ways we can do it, but it's always just inevitably, from math, going to distort some distances. And I like this image from Mike Bostock of many, many different projections at once. So what do? We basically, again, visualization is always an art of trade-offs, and there are a bunch of approaches that we can use to try to make these trade-offs. So they fall into 2 main categories. One is linear approaches, where we're trying to find a good linear projection. Principal component analysis is kind of a workhorse. I realize I don't have authorship on this. There's a paper from 2003 InfoViz, which I feel like is not seen enough, but Yehuda Koren is the author I saw present this, in which they do this brilliant thing, which I don't think is done enough, where if you wanted to, if you have labeled data, you can simultaneously, you can find an optimal linear projection to separate the labels from each other, and it's really effective. So that's another thing to consider. There's also a bunch of nonlinear methods, many, many of them. And you can sort of think overall to, like, what is the goal of each of these methods? PCA is just trying to capture as much variation. This idea of visualization labeled data doesn't have a catchy name. You sort of match the clusters with the projection. And the nonlinear methods generally have some metric of distortion that they use and try to minimize that distortion. So let's take a look at some of these in practice, and then I want to talk a little bit about sort of the theory and how to read these. So let's see. Okay, so what you're seeing here is a tool called the embedding projector that our group created. It's out in the world, open source, and we'll use as our high-dimensional data set MNIST, largely because it's familiar. And this is showing what happens when you do a principal component analysis view of MNIST. And we can do this, make it a little bit more readable by adding a color to this. So now that every digit gets its own color, again, thinking about color scales, we're choosing what the color brewer tool would think of as not sequential or not diverging, but one of these ones is designed to show different categories. And when we do that, we can actually see that PCA does not do a terrible job of separating these things. Like, you can sort of see the ones are all in their area, but then there are a bunch of things that sort of are getting mixed up here. But still, it's maybe a little better than you'd think. However, we can still do better than this if we wanted to look for clusters. In particular, we can look at t-SNE, a nonlinear method. And when we do that, we suddenly get a bunch of fairly well-separated clusters. And we even can start to see things that look like they might be sort of significant. One thing is if we look at, for example, this cluster of ones, you can sort of see there's a slant going on, where on the left here they're slanting to the right, over on this side they're slanting to the left, and it feels like it's starting to capture some sort of useful information. Okay. All right, let's go back here. Okay, the trouble is that, as I said, you can't really get a faithful projection down. And so there's a lot of trickiness. And let's analyze that trickiness. So let's start with t-SNE. This is our main example. So this is a truly beautiful visualization method. And one of the things that makes it work, but also makes it hard to interpret, is it has this adaptive sense of distance. And this is designed to sort of provide a good translation between how distances work in high-dimensional space and low-dimensional space. And also, it does a lot of good things, but it can be tricky. So let's take a look at how you would close read it. So this is based on a Distill article that we wrote. It's called How to Use t-SNE Effectively, and you can look it up. But let's talk about what we did is we said, we'll take some examples where we know ground truth, even in high dimensions, because we'll use completely synthetic data, not like MNIST, but something we truly can understand and control. And we'll look at what happens and get a sense of how to do it. So one thing is that there are hyperparameters in just about all of these methods. In t-SNE, there's a hyperparameter called perplexity, which roughly speaking tells you sort of how big you expect a neighborhood of a point to be, like what a near neighbor would be. And it turns out that that makes a huge difference. So let's take as an original 2 clusters that are Gaussian clusters that are fairly well separated. And let's say that there are 50 items each. And if we create a system like this, you'll start to see something happening. That when perplexity is 2, you don't see those clusters at all. Like they just sort of explode into little tiny pieces. Largely because 2 is such a small number, you're essentially just picking out tiny neighbors of like pairs of points that are very near each other. So you don't see anything close to global or medium scale. You can see at 5, you start to get those clusters out. 30 and 50 seems to do about right, because in fact that matches roughly the scale of those things. At 100, it just goes crazy, largely because if your perplexity sort of matches the total number of data points, everything starts to go wrong. What about the sizes of the clusters, the spatial size that you see on screen? It turns out in t-SNE that means absolutely nothing, and it's really important to keep that in mind. And this is where the adaptive nature of t-SNE can be deceptive. So here the original data set is one cluster that's got a fairly large variance and one that's incredibly tight. Again, with perplexity 2, they just sort of shatter. But then you can see with these other perplexities, for most of the sort of mid-ranges, they actually look exactly the same size visually. And you can view that as either a bug or a feature, depending on your situation. But what you should never do is look at the sizes of things and assume that they correspond to something real. By the way, once you get perplexity 100, in this case I think there's a few more than 50 in each, so maybe 100 in each one, you start to get some vague sense of the distinction in sizes, but it's certainly not a perfect match. Similarly, distances between clusters don't necessarily mean very much, and it really depends on your hyperparameters. You can see with some parameters here, these 3 things on the original, the orange and the blue are very close. They just end up equally far in the middle. Only when you get to very high perplexities does it actually capture them. The other thing is that shapes can be meaningful, but not always. So let's take these 2 things that are sort of various ellipsoids. If you take a very kind of scattered ellipse, not a very dramatic ellipsoid, something that's like twice as long as it is wide, you can see again, for certain perplexity values, you do see the shape. For others, it just turns into something either spherical or shattered. When you have 2 sort of very, very thin distributions next to each other, those actually do stay. As those shapes actually persist. But again, with some slight variations, you can see there's a little bit of spurious curvature as they repel each other. There's this funny kind of twist or break going on and so forth. So it's, again, important to kind of keep this in mind as you look at your t-SNE. So then let's think back on that MNIST example. And I took a couple of screenshots while I was using this tool, and we can see these phenomena at play. So one thing is that if I stop too soon, I get a whole bunch of artifacts that sort of look like this. That's a very classic thing in t-SNE. If you get these weird sort of angles, that means you've probably stopped too soon. But again, let's see what we can guess at and what we can't. So, we have these 4s at the top, these things in pink. Those may not really be separated into 2 clusters. As we saw with the sort of long, thin distributions before, they can kind of break up, even though they clearly were a cluster. At the very bottom, you can note that most of these clusters seem roughly equally far apart. They probably are not. And so that's something we need to keep in mind. The clusters exist, but we don't want to talk about the relationships between those 2 clusters without a great deal of care. On the other hand, the cluster of 1s that actually showed sort of a progression from, tilting to the right to tilting to the left, that was probably a real thing. Like, that thing probably is not just some spherical distribution in space. Okay, so t-SNE is very good, but there's a new kid on the block, and that's something called UMAP. And I just want to give a nod to this briefly. It's something that came out fairly recently. And the idea here is that the purpose of the method is there's a couple of things that it's aiming to do better than t-SNE. So one is simply, from the implementation point of view, trying to be faster. t-SNE is actually fairly, takes a while to actually lay things out. The other thing is that the way that t-SNE algorithm scales is that the more dimensions you're embedding into, the slower it gets. That generally is not a problem for visualization because we only want 2 or 3 dimensions, but if you want to have a pre-processing step where you're focusing down, then you actually might care about that. And also, it seems to capture global structure a little bit better. The way it works, and I'm going to give you sort of a rough description of this, is that it uses ideas from topology and, believe it or not, category theory in order to try to capture the topology very explicitly. It's a little bit like topological data analysis that Carlson has done, but it extends beyond this. Essentially, by doing that, I think this is why it gets the global structure a little bit better. But we can actually compare side by side, or rather the authors of the paper compare side by side how UMAP and t-SNE work. And they do this on MNIST, which we just saw, so among other things. So on the left column here, we see UMAP. On the right column is t-SNE. So in this row here, we see MNIST. And in fact, this looks fairly familiar. This looks much like what we saw in our 3D view. However, here, when we look at UMAP, we actually start to see interesting differences in distances between the clusters. And it actually seems to correspond to something real when you look at things. Similarly, if you look at some of these other things, you can definitely see more global activity, sort of interesting global structure in this, for example, which I think this is word2vec, or some word vector, versus t-SNE. So this is something that's definitely worth doing. I think in interest of time, I will not do a demo of this, but there's actually a very beautiful demo online by Leon Fedden that lets you compare these directly with audio data. And he does a fairly careful analysis, much like the one that we did in our Distill article. So yeah, this is another reference that I would sort of recommend looking at later, something called the Beginner's Guide to Dimensionality Reduction, which lets you sort of compare these things side by side. Okay, there's one last topic I want to talk about while we're talking about high-dimensional space, which is that the geometry is very weird. In many ways, it's quite the opposite of what we learn in 2 and 3 dimensions. So here are 4 statements, and you have to pepper these statements with sort of the usual mathematical caveats, but to a first approximation, they're all true. That, if I pick 2 vectors at random, they're going to be at right angles. A Gaussian distribution doesn't look like a bell curve. It looks like a uniform distribution on a sphere. Random matrices are basically orthogonal matrices. This is something that's, I think, a little bit less appreciated than those first 2 facts, but it essentially follows directly from them. And then one thing which I think is definitely not well appreciated is that random walks in very high dimensions all have the same shape, more or less, probably. And that's a very weird but true thing. And I want to sort of talk a little bit about why that matters in machine learning. So one thing that you see very often is that people will be interested in some process happening in high dimensions, and gradient descent trajectories are a classic example of this. And you'll see so two papers here. There's this really nice paper from Eliana Lort on visualizing deep network training trajectories, in which she finds these very interesting kind of Lissajous patterns. If you do PCA on the weights. And similarly, there's another recent, very interesting paper about the loss landscape of neural networks. And they too are sort of projecting by PCA basically the training trajectories. And in each case, you see they get these kind of things that look like parabolas, essentially, roughly speaking. And the question is, what can we read into that about training? And the answer is it's not clear what we can, because it turns out that if you look at a random walk and project it by PCA, you will actually see exactly these same basic phenomena of Lissajous patterns, that essentially the principal components when you project down look like cosines. And this is, again, there's a bunch of ways to see this. There's a recent paper from Antognini and Sol-Dickstein that shows this. This is where this diagram is from. And it's a sort of a shocking fact, because we think about random walks as these really weird, jittery things, but that's low-dimensional thinking. So one general thing is that whenever you're doing this kind of visualization of sort of anything in high-dimensional space, compare with the most random baseline you can, and it'll probably bear fruit.
All right, so bringing high-dimensional space and visualization together again. Let's take a look at a quick demo. So we were curious about working with a research model, a true research model at Google, and we ended up working with some of the folks who were doing multilingual translation. And there, some of you may be familiar with this, it was the first time that, in this case, Google came up with a translation system that could take as input multiple languages and could output translations into multiple languages without having seen training data on all the pairs of languages it was translating. So in other words, if you look at this slide, imagine a system that has trained on sentences that are translated between English and Japanese and English, and then also English and Korean, Korean and English. Okay, that's the training data. That's all the training data. And then all of a sudden, the system can start outputting high-quality translations straight from Japanese to Korean and vice versa, without ever having seen a single sentence directly in those directions. Okay, so part of the question there was how are these systems doing this? And so to look into that, we decided to visualize, the way these systems are set up. There is the encoder, there is the decoder, and in the middle there's an attention vector. And so we decided to visualize that attention vector. So just very briefly walk you through what might a visualization like that look like. Oh, and before I do that, let me actually step back and tell you about the research questions the scientists had. So when we talked to them, they were saying, we don't know how these systems are resolving the multilingual space of embeddings. Is it that the system is doing something like what you see on the left here, where imagine I am coloring each language in a different color, right? So you have English is blue and Japanese is green and Korean is yellow and so forth. Is it that my system is, creating an embedding space, all of English in one corner and all of the Japanese embeddings are in the other corner and all the Korean embeddings are in the other corner, and then it maps between these spaces? Or is the question, is what's happening more like what you see on the right, which is a little bit more of a mess, but where the system is bringing together these different languages, and in bringing them together, it's doing something where it doesn't care as much about the string home being different from the string casa. It really cares more that these are semantically related. So is the system paying attention more to the semantics of these words versus paying attention to what languages it came from? So in order to answer that question, we decided to work with a visualization. Imagine I have a sentence like, the stratosphere extends from 10 kilometers to 50 kilometers in altitude. Okay, that sentence may look like this, okay, in embeddings space. And I have all the words there, and then I connect those dots in high-dimensional space. And voila, this is my sentence. Now, when I translate that sentence into another language, in this case here, Portuguese, does my embedding space look like this, where English is in one corner and Portuguese is on the other corner? Or does it look more like this, where the two languages are kind of put together, right? And so to give you a big reveal, let me show you what we did with the embedding projector. So this here is a visualization of a multilingual system that takes in 3 languages: English, Japanese, and Korean. I am coloring sentences here. Each sentence I'm coloring in its source language. So English is blue, Korean is red, Japanese is yellow. My first question is, it looks convoluted and weird, but my first question is, do you see a big neighborhood of red in one part, a big neighborhood of yellow on another corner, and a big neighborhood of red? Do you see separate colors? No, right? You don't see this. So the first time we saw this, we're like, ooh, this is interesting. Okay, so then we're like, this could be an interesting sign. So then, let me start looking at my favorite sentence here. I'm going to highlight that sentence. The stratosphere is in the range of 10 to 50 kilometers. And when I highlight this on the embedding projector, it highlights for me, and here's my list, all my nearest neighbors. And as you can see, as I mouse over these nearest neighbors, independently of the language, all of these nearest neighbors are in the same cluster, okay? So this was huge because this told us that these were the first indications of a universal language, of an interlingua that these systems were actually coming up with. And this was part of why they were able to take as input multiple languages and output multiple languages. So this was major, right, to answer the question that the scientists had. Now keep this image in mind, as convoluted as it is, and I want to show you the same visualization of a sister system. So we're going to go back here and suspense, we're going to look at this system. Look at this image on the left. This is the same visualization of a system that does Portuguese, English, and Spanish. The difference here is that I have a big chunk of red hanging out by itself. We're like, what's going on here? We thought these things were clustering, right? So this big chunk of red, what we did is we downloaded all of those sentences and we ran a statistical analysis. Visualization, statistics. We ran a statistical analysis of the quality of the translations of these sentences, and the quality was bad, okay? So why does this matter? It matters because it tells me that the geometry of this space really matters. And if your system is not being able to do that thing where it clusters these multiple languages semantically, it's not working well. So you're going to have to go back and debug your system. So again, this hopefully illustrates one notion of interpretability, but also one start for debuggability. Very quickly, I want to end on one other note that I think is important. Visualization for machine learning in terms of education and communication. I'm going to go very fast here. There are 2 different audiences where you can be really effective with visualization from an education perspective. One is technical audiences, so things like the TensorFlow Playground, a lot of the work on Distill, but also education and communication to non-technical audiences. And that matters a ton when we're talking about machine learning, because there are other stakeholders other than technical people who should be paying attention and thinking about machine learning. So a couple of examples here. This is a visualization we did to illustrate some of fairness, machine learning fairness trade-offs. And so we took a ton of math and we transformed that into an interactive visual simulation that people could play with. It turns out policymakers, regulators loved to look at this because they felt like they were learning, they were getting to a ton of really core mathematical concepts without having to do a PhD, but without having the message dumbed down to them, for them, right? So it was really, really good. One last thing about Quick Draw. This is really cool because it explains how machine learning works for kids. So imagine the system asked you to draw an avocado. It shows you what it thinks an avocado is by giving you a ton of examples of other drawings. And this is when it asked you to draw a bee. It didn't guess the bee, but it thought it was either a sea turtle, a mouse, or a shark. So it's showing you, it's visualizing your output on top of other people's drawings. And then it shows you what it thinks about when it thinks about a bee. Okay? So really informative without having to be super complicated. Okay, I think we're going to...
Yeah. So we're going to end there. I think there are, to recap, there's a huge amount of knowledge already about how data visualization works that you should take advantage of. I think when you think about high-dimensional spaces, again, this is a very active area. Understanding the issues around, what random walks look like, help you interpret those other things. There's a lot of directions to go. We wanted to leave you with these resources. These are just a few of some of the things that we've looked at for sort of both understanding, learning, tools, and so forth. And with that, I think we will end and open to questions. Yeah.
Are there any questions? I think there are 2 microphones here.
I have a question. A lot of the visualization you show were images, for example. Have you seen any work on videos to show the temporal also at the same time as the special features?
Yeah, video is a tough one in general. I think there has been work in the data viz world on visualizing videos, often historically in the context of, say, editing a video, trying to find your place. I honestly don't know of anything that I feel like has solved the problem. I think this is actually a great example of an area where there is much more research needed that you've spotlighted, yes.
Thank you very much.
In the slide with Spanish, English, and Portuguese, I'm curious, you said the training data was bad. How did you know it was bad, and how did you measure that?
So we didn't know that the training data was bad. What we did know was that afterwards we ran an analysis of the output translations. And there is a blue score. It's called the blue score for those translations, and that's what we were looking at. And so that's what led us to the conclusion that, oh, wow, this whole neighborhood here is not doing well. It was based on the score. We had ground truth. Yeah.
Thank you.
Sure.
Thank you for your presentation. Can you hear me?
We can't hear you.
Thank you for your presentation. I want to know that educational and communication is so important for visualization. How about we make some visualization that motivate people to learn machine learning? From a very complex problem, we just show attractive visualization so people that have not enough knowledge in machine learning just attract to learn about machine learning and produce something like that.
Yeah, I think that's a great question, sort of how you motivate people. I think there's actually something from the Google Creative Lab called Teachable Machine that has, I think, lets people basically train a machine, their own laptop, to recognize themselves waving or doing something silly, and it's done in a very fun way, and I think it has exactly that motivational question. I think another thing, frankly, is I think a lot of the work with GANs has been motivating various communities to learn more about machine learning, partly because it seems so mysterious and magical. So yeah, those would be two examples.
Thank you. Thank you.
Hello. So one of the main takeaways from the talk that I got, at least, was that high-dimensional space is really unintuitive to try and visualize. Do you have any recommendations as to like a hitchhiker's guide to high-dimensional space?
Yeah, I think that is a great idea. I've often wished something like that existed, because it's exactly this question of one of the things I feel like would be nice if every visualization came with is an example of what it looks like with random data. And then you can understand the difference. So for example, in the papers I showed from Lorch and Lee, if you go back knowing about random walks, what you notice is that those trajectories look a little bit like random walks, but not exactly. And it completely changes the way that you interpret them. When you first look at them, the naive reaction is, oh, those look like parabolas. When you look at them again, having carefully seen, your reaction is, oh, wow, they're not exactly parabolas, and the ways that they're different are really informative. So I strongly believe there should be sort of a textbook of the peculiarities of high-dimensional space, yeah.
I see, but you don't know of any sort of cohesive resources for something like that?
I don't. There's sort of some interesting YouTube videos if you look up high-dimensional space, but, and certainly, I'm trying to think if there's any single one that I recommend. Yeah, but someone should do that, for sure.
Awesome, thank you.
Hey, thanks for the nice talk. So are there any techniques for high-dimensional spatial and temporal data sets? So if you have something like something varying on a map over time, so you have like TSNE for high-dimensional data sets, right? Is there something you can visualize in that embedding space for spatial and temporal variations?
Wait, I'm sorry, can you repeat that last part?
So you have a TSNE type embedding space, right? That's for a sentence. So if you have something varying like in sentence and also in time. So let's say I want to visualize multiple sentences. Let's say the same sentence spoken in different languages over time, right?
So sort of a time-varying embedding, essentially.
Yeah,
So there is a thing that you can do in the embedding projector that we showed that lets you at least visualize trajectories through space. I think it is very tricky. It's hard to make sense of. Sometimes, I think this is also a case where small multiples are very good. So there was a paper out of Stanford showing how word embeddings change over time as you look at, say, books from different decades. And there, I believe they use small multiples. I don't know of a solution more sophisticated than that, but I would say that's another great area.
Yeah, that's what I was going to say. That's a great area. If you're interested in working with visualization, coming up with a visualization technique that allows you to compare 2 or 3 different embeddings.
Yeah, so
highly needed.
I work on the physics data set, so it is spatial and temporal variation. That's what I was curious about. I work on physics data sets, which has spatial and temporal variation. That's what I was curious about the topic. Right, thank you.
Sure.
Thanks for the talk. You've shown very nicely the influence of the hyperparameter for TSNE. You've shown the hyperparameter influence for TSNE and the perplexity. Is a good rule of thumb to say that if you don't see any clusters for any value, to say there is no cluster? I mean, you've drawn that conclusion at one point.
So you're saying if you don't, is it a good rule of thumb to say that if you don't see any clusters for any values, then is it safe to say there are no clusters?
Yeah.
Is that the question? Yeah.
My guess is you could probably construct a very weird data set that did have some cluster that would not show up, but that is a good question. I think in practice, I have to say another issue with TSNE is that it can make random data look non-random at times if you're not careful. And so often it feels like the issue is much more about false positives than false negatives, in a sense, when you're looking for clusters, in my experience.
And the other thing to think about is it's always nice to kind of sanity check. You're not going to get like the perfect answer, but to sanity check with other projection techniques, right? So for instance, in the embedding projector, for instance, it comes with 2 projection techniques. So one is linear PCA, the other is TSNE. We're hoping that soon we're going to have UMAP. But basically, the more you turn and look at these things and try to, just try out a bunch of stuff, the better. But you're right. There's no like, ooh, now I'm 100% sure. Yeah.
All right. Thank you.
Thanks for a great talk. One question. Is it possible to share the slides?
Yeah, we'll try to share something as much as we can. Yeah,
We will. Yeah.
Thank
we
you.
will figure out what is the best way. Yes.
Hi. It was a very nice talk. So I have a data set I'm trying to visualize, which is spatial and temporal. And I was thinking of going with an animation for the time dimension. Would you advise against that? Because I didn't see you doing that in any of the visualizations.
I would say it depends on your purpose. I think for exploratory analysis, animation is actually often kind of problematic. On the other hand, if you're going to use it to explain your ideas or try to get funding from someone, then animation is excellent for that. That is my most practical advice.
But also, you could give it a try, right? You could do something with animation, but then you can also take a bunch of screenshots and do small multiples. And depending on your analytical task, what it is you're trying to get at, you can decide which one do you think is the most effective. If you think about one of the ones we showed from the New York Times, where they were trying to show drought over time, it was quite effective to have all of those things at the same time on the screen.
Thank you.
Okay, thank you for your presentation. And you show that your word range model cluster is quite mixed, right? But in my intuition, there must be some similarity and dissimilarity between the languages. So is that can be interpreted in your visualization, or my intuition is biased?
So let me make sure I understand. Is your intuition that the languages are similar?
My intuition is like this, and Korean and Japanese is quite similar than Korean and English. So can it be interpreted in your visualization?
So without being a native speaker, I had no idea. I thought that Japanese and Korean was quite similar. I am told from other people who speak Japanese or Korean that they are quite different. But even keeping that aside for a moment, I'm a native Portuguese speaker. And so when I looked at that system that had English, Portuguese, and Spanish, to me, it was very clear that those things should have clustered. Because Portuguese and Spanish are really close. I'm like, this is going to be so easy. And it was not. It did not cluster. Right? So that to me was the point where I was like, whoa, what's going on here? So even, languages that should be quite similar are not necessarily clustering. So I think that's where I was like, oh, this is very complicated. It's not always about similarity.
Thank you.
One more question.
It's on? Sorry. Thanks for your great sharing. I have a very practical question. Normally, how long it takes to get a conclusion, and what's the typical workflow when you have a research question in Google Brain?
Can you repeat the question?
Yeah, basically it's very practical. What's the best typical workflow in Google Brain when you have a research question, and how long does it take to get a conclusion for your research?
Oh, how long does a project last from the... It's impossible to give an answer to that, because I think it is there's so many people doing so many different things that I think sometimes there are very quick experiments people do. There's other things that take years. I think, to me, actually, that's one of the pleasures of it, is that things do happen at all different scales, and I think that's actually very exciting. So yeah.
Last question.
I have a comment, so it's technically not a question. I thought it was a really great job, especially the first part. I hadn't thought of the psychology. But in my lab, we developed visualization algorithms, and I just wanted to point out, you guys didn't really cover diffusion maps, which are really good for trajectories and things like that, which are cool. B, we have a method called PHATE, P-H-A-T-E, and we feel like it's much, much better than UMAP at capturing global and local information. Please check it out, and it's faster than UMAP.
Awesome.
Thank you.
Thank you.
Thank you all.